In this video, we are going to find the center of mass in SolidWorks. And even though I've got some 2D bodies here, I recognize that that's actually technically the centroid, but in SolidWorks, it can't do anything in 2D. So we're going to go ahead and call it a mass because it will be a center of mass by the time we put it in SolidWorks. But I'm going to solve basically 3 different problems. First of all, I'm going to do a composite body problem, and then an equation-driven problem, and then a problem with variable density, where you have kind of like an assembly with 2 different densities for the 2 different products or parts, and that'll be great. We'll solve it by hand, and then we'll go put it in SolidWorks. And we're doing 3 in this one video because it's usually pretty straightforward to do this in SolidWorks. It's kind of super fast, and the math is pretty fast too. So, as you probably know, maybe, for finding the center of mass in a composite body, basically what we're going to do is create a weighted average. So I'm going to start by finding the area of that section. I can say, well, that's 2 times 1, which is, 2. And its y location is at -1, or x location is at -1. Then I want to add in the triangle, which is 1/2 base times height. So that's just going to be 1/2. And its x centroid is located 1/3 from the fat side, which is just 1/3 from the origin, but again, in the left direction. Then I got this guy who is a 2 by 2. Yeah, 2 by 2. So his area is 4, and he's located at 1 from the origin along the x-axis. Then I'm going to move this over because I'm running out of space. All right, let's do one more. This guy here, now notice I'm going through the circle, even though that's a hole, we'll take care of it later. 2 times 3 is 6, and 2 plus 1 is 3. So its center is there at 3. Now I'm going to subtract off the area of the circle, of course being pi r squared, and r is 1/2, so s squared is a 4, so pi over 4, and its center is right there at 2. There we go. All right, so again, we're finding the centroid in the x direction. And so now that I have those, all I need to do is divide by the total mass. So 2 plus 1/2 plus 4 plus 6 minus pi over 4. And I plug this into my little calculator, and I get something along the lines of 0.854. That doesn't make sense because that would put it over there. That seems a little lopsided. Hold on, let me look at this. Oh, that's because I am looking at the wrong part of my paper. It's actually 1.56. There we go. Okay, 1.56. That actually looks a lot better. That's closer to where I would have expected it to be. Excellent. Okay, now let's see if we can go ahead and take care of this for the y. All right, so our y is going to be pretty much the same thing, area times the y center. So the center for the y is, of course, at 1/2. And then area, now this guy's at 1, and then 1/3 more, because it's a triangle still, so 1 and 1/3 more. Then we have an area of 4, and its height is at 1, because it's 1 off the bottom. Then the area of 6 again, and its height is at 1.5. Then again, we're going to subtract off the pi over 4, and its y center is actually located at 1. And again, divide by the full mass or area, plus 6 minus pi over 4, and we get 1.18, and there we go. So that actually looks pretty good, kind of where I'd expect it to be. It's a little bit above the center. So 1.56, 1.18 is going to be the answer we're looking for in SolidWorks, and that's going to be located just about right there. So that's what we're looking for. Now we're going to do one of these that is equation driven, and that's good. And it's not particularly complicated, just if you've never done it in SolidWorks, it might be a little bit weird. All right, so we're going to take a look here. And essentially what we're going to do is we're going to draw a little D area. And we can do it vertically or horizontally. It just feels like doing it vertically today. And so we're going to call this our D area. And our D area has a height of y and a width of dx. So our D area is going to be y times dx. All right. The next thing we want to do is we want to label the center of our D area, and at any given time it's going to be at x, and then, because wherever it physically is at x, and then actually at y over 2 is where the center of that's going to be. So just want to make sure that we know that going forward. Okay, the next step is to actually set up the integral. So this can be proven, but that's not the purpose of this particular video, is that the center is located at x, integral x dA over the integral dA. And now it's not x like as in the variable x, but like x the center of your dA x, which in our case is still just x. So make a note of that if you like. So now we're basically just going to plug in the values that we have. So since we know that y is equal to 10x over x squared plus 6, that means that we can actually write the whole integral in terms of x, which is nice because that means we can actually solve it without too much problem. So our integral from 0 to 3, x times 10x, x squared plus 6, dx, all divided by integral 10x, x squared plus 6, dx. Yay! All right. And I'm going to go ahead and do the bottom part because that's actually going to show up in both of the, whatever you call them thingies, equations that we're going to do here. And because I'm excessively lazy, I'm going to do this on my T89. So I'm just going to start off, so the 10x divided by x squared plus 6, and there we go. Now I'm going to integrate, so that's the yellow 7 key, integrate that with respect to x, comma, 0 to 3. There we go. So that's the, well, we get an actual numerical value. So that's the area basically of that shape is 4.5, what was it? 4.5 something, 4.58. Alrighty. Now I'm going to do the top, which is basically the exact same integral, except it's going to have an extra x in it. So I'm just going to, rather than retype it, I'm just going to fix it. So we've got an x squared in there now. And there's the top, 8.30. And then I just divide them out. And hold on. Divided by that is 1.81. Beautiful. All right. So 1.81, that is the physical location of the center along the x-axis, or along the x direction. Yay! And again, there's y, and it's y dA. And remember that it's not like the official y, it's the center y. So remember that the x was the center of the dA, and this is the y that's the center of the dA. So it's a little weird to look at because it's not really y. It's, in our case, it's actually y over 2, because that's where the center of that rectangle was. In the y direction was at y over 2. So it just looks a little strange. And I'm just going to go ahead and plug this in. We've got 1/2, forgot what it was. There we go. So y was just 10 over x, or 10x, x squared plus 6. And then we've got the dA. Oh, this guy right here is the y over 2, so don't get that confused. And then we have this part here, which is the dA part. Wrong color. What would the neighbors say? dA divided by integral this thingy, which we already calculated, but I'm just writing it out because it makes me feel better. dx. And 4.58 on the bottom. And then I'm going to put it in the calculator. And my calculator says it's, well, hold on. It's basically the same integral, except it's going to be 5x squared. Yeah, 5. And then x squared. And then the bottom is also going to be squared. But other than that, it's the same integral on the top. And there we go, 4.04. And let me go ahead and put that in there. And then I'm going to divide it. And everybody's going to be so jealous because I know the center of this thingy. And it's 0.883. So I've got 1.81 and 0.883. And if I look at my picture, that's kind of weird because that's kind of where I actually drew it to begin with, because we're close to the, that's not the right place, because we're closer to the 2, so it's kind of a little bit below the center. So, you know, that's where if I put my finger, I could like balance it like a really fancy waiter or something like that. So there's the center. All right, now we're going to do the variable density just because it's kind of cool. So we're going to do basically an assembly in SolidWorks in a minute. But first of all, we need to find the weight of each of the blocks. And that's super not hard at all. Just for the main block, it's know its volume, 2 times 3 times 1, times its density, 1.2, times the gravity thing, 9.81, and you put this in your something or other and get an answer. And now we're going to do the weight of the wedge thingy, and that's going to be 1/2 base times height and then times the depth. So we've got 1/2, 1 times 2, or 2 times 1, and then multiply by the depth, and then times its density and the gravity thing, and now we have the weight of the 2 blocks, which is great. Okay, now we want to actually find the center of these guys now. So basically we just need to do this along 3 directions now instead of just 2. So remember, x is in this direction, so x for the block is 1.5 over, so we're going to start with a 1.5 and multiply it by the weight of the block. And then if we look at the triangle, make sure that this kind of makes sense, but the triangle is going to be at 1/2. So kind of think like if you come halfway in from this direction, it's kind of like symmetric on both sides. If you come in at 1/2, I hope that makes sense. It's depth, because that's not the triangle side. From the x direction, it's just whatever. And we divide by the weight of the whole thing, and we get 1.06. I'm not going to make you watch me type stuff into the calculator for this one. All right, and then for y, again, remember y is in that direction, so that's at 1 times the weight, and this is actually going to be 1/3 from the fat side, and it has a length of 2, so it's 1/3 of 2 times the triangle, divided by the weight of everything, weight of the triangle, and we get 0.854, yay! For z, let's scoot down. Z deserves her own space. All right, so for z, and remember z is of course going up, so we've got 0.5, or 1/2, and then this is going to be 1 up, and then 1/3 of 1, so here we go, triangle, that's a triangle, and divide by the weight of everything, and we get 0.0865. So those are the answers we're going to be looking for when we put this in SolidWorks. So now we're going to have some fun in SolidWorks, so create yourself a part. It's going to be very exciting. Yeah, alright, so I'm going to sketch off the front plane, and I'm just going to draw that first image. Make sure you start at the origin. This is one of those things where the origin really matters, because the center of mass is of course relative to where the origin is, so if your origin is in the wrong spot, it's not going to work. Make sure that this line is horizontal, uppity-doo, uppity-doo, uppity. Make sure those are collinear if you can. We can fix it later. Do-do-do-do, do-do-do, and do-do-do. Beautiful. Alright, now I'm going to dimension some things. This guy is 2, and this guy was 1, and this guy was 1. 1, come on. 1. And this guy was 2. And this guy was 2. And this guy was 3. 3. And here to here was 1. And this really should be done by now. This guy, and so control click this guy because they are vertical, and now we're good. Beautiful. And if you want, you can go ahead and put the circle in there. I think so. I'm lining it up with that 1. Oh, look at that. Look how pretty she is. Now the radius. Oh, it's doing the whole diameter. So the diameter is 1, because I'm really good at dividing and multiplying by 2. So this is at 1. And this here is at 2. Thank you. Fully defined sketch. Extrude it. Wait, why do you say that I'm not fully defined? Okay, I fixed it. Alright, so I've got this fully defined sketch. Now I'm going to extrude it. This thingy. Extrude this thingy. Beautiful. Oh man, it didn't extrude my little whatever thing you call those circles. That's alright, I'll just leave it there. I could just go ahead and put another one on it. So normal 2, I'll just put the new guy on here, and I'll just put the circle on again. Circle of radius 1, because this is not a SolidWorks tutorial as much as a, well, it kind of is. I'm just messing around. I'm just having a good time, like all girls do on a Saturday night, doing SolidWorks centroids, because, you know, how I roll. Alright, now I can just do the extruded cut and make sure it's through, and it's beautiful. There we go. Alright. Now, believe it or not, it's super straightforward. At this point, all I have to do is go to Evaluate, find the mass properties, and then I get the 1.56 and the 1.118 versus 9. That's okay. That's a very small, whatever you call it, thingy. Very small error, percent error. So 1.56, 1.18, 1.19. So that's exactly what I expected it to be. And this should definitely not be a huge shock. So there we go with that one. All right, let's do the next one. I'm going to create a new part, and this is the one that's going to be super annoying because you'll be like, I had to do calculus before, and now you're doing it with no calculus. So essentially what I'm going to do is I'm going to do an equation-driven curve. All right, so if you remember the equation that we had, it was 10 times x divided by x squared plus 6. And if you've never done something in here before, it's very similar. So like the square root function is just that, and the sine function is just like that. So basically we have this, and we're going to say it's going to go from 0 to 3. And hit F to center it, and there we go. Now this is actually lovely, because now all we have to do is close off the curve, and there, and here, and this distance is 3. Oh, I don't have to put that in there. Okay, great. Now, as a note, the first time I did this, for some reason, even though I had a 3 on here, it was going to like 2.8 something or other. So basically, you can unlock this and then change the endpoint and then dimension this. So if you don't like, if the endpoint isn't going in the right place, you could leave it unlocked and then dimension the 3 there, and then it would be fully defined again. So just kind of as a heads up in case that happens to you. And then all I have to do at this point is extrude it and look at the mass properties. And it's really that fast as I get the 1.81 and the 0.88. I don't see the 3, but that's okay. I could adjust that in the units if I wanted to. But that's the one that's super frustrating because you're like, but calculus versus just pressing buttons. So there you get that one. All right, so let's go to the one that's going to be a little bit more fun, which is the wedge and block thingy. So essentially what I'm going to do now is I'm going to create 2 parts and make an assembly. So from the front plane, I'm going to create that 2 by 3. And again, I need to make sure that, actually, let me make it from the top. So let me sketch from the top plane. So if I'm looking at the top, I think that I'm going to come this direction, if I'm visualizing this correctly. So this over here is going to be 3, and this here is going to be the 2, and then I'm going to extrude it up by 1, and let's just make sure that that origin is in the right place. It should be in the back corner. Beautiful. Okay, now something we've never done, or haven't done, is we're going to go up to the options, and we're going to go to the document properties, and we're going to change the material properties, and instead of being, well, first of all, make sure your units are right. You want to make sure you're in MKS. But then you're going to go in here and you're going to change it. And you're going to say this is going to be 1.2 kilograms per cubic meter. And then click OK. All right, so now you have this, and we're going to go ahead and call it the block. Okay. The next thing we're going to do is we're going to create the triangle. And this one I'm going to do from probably from the front plane. And I'm going to create my little triangle. Boop-a-doo, da-doop-da-doo. And it really doesn't matter if the origin here is perfect because I can just align the origins in the sketchy thing, in the assembly. So that's 1, and this is going to be the 2, and then it's going to extrude forward by 1. And then I'll come in here and I'll again change my options, making sure my units are MKS, and that this here is going to be 5.6. So mostly I just want to do this because it's kind of neat. I'm going to save this as a triangle. All right, and now I want to create an assembly. And I'll start with the block because it's on the bottom. And sometimes it just takes a minute. Don't get too impatient. Again, making sure the origin's in the right place and it's fixed. So that's good. Now I'm going to add another component of the triangle, just right there on top. Isn't she cute? All right, I'm going to mate this guy, control click there, and the mate should pop right up. And then scroll around, this guy to this guy, mate. And again, you can hold the scroll wheel and rotate around, or you can just go back to here. All right, but I need to touch this one, and mate. Now I should have a fully defined, nothing's wiggling around kind of thing. And go ahead and save the assembly. And theoretically, if the origin is in the right place, but it's not. Okay, so see how the origin is supposed to be right here, and it's not. So what I need to do is I need to float that so that I can move it to where this guy and the origin, so I control click the origin, mate those, but now you see it just wiggles. So I want the front plane and the other front plane to coincide, and then now it should just rotate in one direction, so I just have to align, say, the top and the top, and that should do it. Now everything is fixed again, and the origin is back in the back corner where it's supposed to be. Origin is back there, perfect. So now if I evaluate the mass properties, I get the 0.854, the 0.865, and the 1.06. And you're like, well, you had XYZ or ZYX, these are in a different order. That's just because if you look at the coordinate system here, see how it has the y going up and the x going out. So their z is actually my x, which correlates exactly with what they had. So their z is my x, and the other two are messed up too. But we can get the exact same thing. So the trick on this was just to go in there and mess around with the density from the properties section. So that was fun. I hope you learned something.